Hello, everybody. Depending on where you are, a good morning, a good afternoon, or a good evening. My name is Vijay Kulkarni, and to the right is Srinivas, my colleague, who will be presenting today our VoIP ATM test solutions. Thank you for joining this webinar. So, we are GL Communications, and we've been in business, as you can read here, since 1986. And we are specialists in telecommunications and telecommunications hardware and software. That's our specialty. And we've been honing that expertise for more than 30 years. As you can read here, we have a consulting branch that helps us in the same area, telecommunications. Primarily, we do a lot of transit consulting, telecommunications for transit agencies, for agencies like NASA and U.S. Coast Guard and so on. But we also build, and this is our exciting part of our company, test and measurement equipment, and in all technologies, wireless, voice over IP, here ATM, I'm talking about asynchronous transfer mode that preceded IP, SONET, SDH, TDM, even analog, where we began from. And our products are rich in analysis, emulation, and conformance testing. And I think one of the key features of our products are its visualization. We present data in a visual manner. We try to show the source signal in its native format. We have a large capture capability, all of our test instruments. They can capture for days, months to years. And it's portable as well as cost effective. Okay, so today our agenda is to present our methods to test, measure, and analyze the various elements in this new VoIP architecture for ATM voice services. As you know, as this picture depicts, ATM architecture consists of VCSs, voice control switches, ground radio stations where the actual signal is transmitted to the aircraft between air traffic controller and the pilot. It consists of recorders that actually record the whole voice session for safety and diagnostic purposes. It also encompasses gateways, which is not shown here, but which is probably an element of the transitioning network. It also consists of analog radios, IP radios, which are coming out these days, and also remote radio-controlled equipment that is situated remotely that must be controlled due to remote access. As you know, the core of the new architecture are ED137 standards for radio, telephone, and recorder elements. And those performance metrics are conveyed in ED138 monitoring solutions that specify the voice quality, the delay, and the functional performance. So one of the driving factors for this transition is the fact that the wide area network is transitioning, the carriers are transitioning from lease line technologies in TDM and analog domain to IP. So that's a critical driving factor. And the other driving factor are these standards. The FAA, EUROCAE, many ANSPs are demanding that the equipment be interoperable. So these are two driving factors in this transition to the IP domain. And in addition, the network has to satisfy the performance that it currently has. It has to either equal or exceed the performance. And for that, ED138 lays out the performance metrics for delay. We're talking about the push-to-talk signal as it transmits, as it's transported to the remote radio station, or squelch, for example. There are many, many other critical signals. And the voice quality has to be equal to or greater than the TDM environment. And for that, we also have a test and measurement suite that can consist of various elements that allows us to measure the delays and performance of these networks. Okay, Srinivas, would you like to tell us a little bit about our architecture for our emulators, recorders, and also our critical delay measurement suite, all based around what we call MAPST, Message Automation and Protocol Simulation. This is a key feature of our product suite. Srinivas?
Yeah, thanks, Vijay. Hello, everybody. So this MAPS framework is used to simulate like all our ED137 emulators like radio, telephone, and recorder. And yeah, the name says like the message automation and protocol simulation. And this framework is also used to simulate protocols across analog, TDM, VoIP, and wireless technologies. So as the name indicates, it provides a complete flexibility to create and modify the messages and scripts to achieve all kinds of custom test scenarios, whether it could be like a valid test cases, invalid test cases. And basically this framework uses a very simple, easy, and but at the same time a very powerful scripting language which can be learned very easily to create your own custom scenarios. And it also allows multiple endpoints to be simulated, basically like end users, which can be used to generate bulk simultaneous calls.
Okay, so Srinivas, I'd like to add one thing back to the same slide, and that is the architecture. It lends itself very easily, and we provide APIs for Python, Java, C#, and even REST APIs. So the MAPS architecture allows you to incorporate this measurement suite, either the emulators or the delay measurement equipment, into your own test environment, into your own measurement suites.
Yeah, thanks, Vijay. Okay, so we'll begin with the radio emulator. So basically, it is a very lightweight software product, and it has a very user-friendly graphical interface. It runs on the Windows platforms like Windows 7 and up to Windows 10. And it also comes along with CLI or API accesses for seamless integration with the third-party test tools. As you can see here, this MAPS ED137 radio is used to simulate the controller working position, or it can be used to simulate the ground radio stations. And yeah, all these simulations are according to the specifications ED137 1B and the latest one ED137 1C radio interfaces. And as I told, like we can simulate the multiple end users, so we can simulate multiple controller working positions or ground radio stations in a single instance of the software. And since they are very lightweight, they can be comfortably used. They are very portable and comfortably used to perform the field testing or even factory acceptance testing, those kind of scenarios. And it supports all the radio types and the PTT types, the radio types like radio TXRX, radio idle, coupling, and receive only calls, PTT types, all the 5 PTT types like test, normal, priority, emergency, and coupling. And it will also allow you to configure all the SIP headers and also the mandatory or optional SDP parameters specified in the specifications. So each end user can be configured with all these parameters. So that speaks about the flexibility it gives. And it also supports the important features like link session management, WG67 key in event, multicast routing, and the cell call tone transmissions. And apart from that, we can even simulate as a remote radio controller equipment to handle the radio remote control commands coming from the device under test. And we can also simulate the RRC commands also if we are acting as a CWP or a VCS.
The ED137 emulator the heart of it is these profiles. So the part of our MAPST architecture is allows you to emulate from one call to actually tens of thousands of calls. And that volume capability, that the range of capacity is driven by something called profiles. So each ED137 radio emulator or the telephone or, for example, any other MAPST products, ISD and SS7, are all driven by what we call profiles. A profile provides all of the specifics associated with that emulator. And here we're showing you, in particular, for ED137, the radio emulator could be the CWP or the GRS, and it would have all of these specifics associated. Here we're showing you the CWP profile and the specifics associated with that. Now, of course, at the CWP, we want to be able to control the PTT and the PTT type. So you can see here in this slide that the PTT is all of the different variations of PTT, which are radio idle, receive only, transmit, receive, coupling, so on, are available. You can set that profile. There can be many, many profiles. So the number of profiles is actually up to you and the capacity of the system that is the ED137 emulator. It's essentially only software. However, we provide it in a port. You can install it on a laptop and use the onboard NIC, the mic, and the speaker with a 64-bit OS. That's what we recommend. You can do that, or we can supply you an appliance where ED137 is pre-installed and you're ready to go. So, but you can build your own profiles, and these the number of profiles that you build will dictate how many simultaneous sessions that you might be engaged in. The codecs, we have a variety of codec options. We also provide the capability to prioritize different messages, like the PTT could be prioritized to have a higher priority, or the voice packets could be higher priority using the DSCP, standard DSCP parameter. And one of the most important features is that once you have these control capabilities, you can also take either manual or automated traffic actions. And that means send and record to file, send digits, tones, talk using the microphone, built-in microphone of the platform, play to the speaker. So it provides a very easy to use. These can be automated as well as manually controlled. We'll show you the GUI in just a few minutes. The other thing that you can do, you can actually, in a test environment, you can introduce impairments in an automated fashion, like, for example, like packet loss, duplicate packets, out of sequence, and latency. You can actually introduce latency into the system rather than having maybe perhaps a WAN emulator. We'll show you both later down the road here. And Srinivas, can you take this one?
Yeah. So here actually we are showing the air to ground calls established to these ground radio stations. So this is the call reception window here. Okay, so I'll just try to brief you what are these elements. So basically this SIP call control.gls is the script which is emulating all the air to ground scenarios. And you can see the call is landed on ground radio station 1. And the call is coming from the particular CWP03 controller. Okay, and this is the button which is used to execute the script or stop the script. And as and when the call progresses, we are going to update the status on the call, like what is exactly happening. For example, whenever the squelch is turned on, so it is going to say like squelch is being transmitted. And these are the event buttons. Basically, it is like this is the button to apply the squelch or turn off the squelch here. And apart from that, we also have the results column where user within the script, he can define what is the pass and fail criterias. So those things, as and when they encounter, the appropriate results can be logged to this column. Okay. And apart from that, you are seeing these event buttons here. Okay. On a particular selected call, we can apply certain events. For example, I may opt to receive this traffic, like I want to record the audio coming in, or I can apply the signal quality index, okay, which is configured in the profile, okay, or I can enable the synchronous call transmission feature. I can put the GRS under summation mode, PTT summation mode. Like as Vijay told, like we can even apply the impairments when we are doing the squelch. The audio packets are being sent towards the CWP, and during that one we can introduce some impairments like packet loss, jitter like this. And we can also play the incoming PTT to the speaker. Such event buttons are provided. And apart from that, you can see here, for the selected call, we are displaying the complete message sequences. So these message sequences include the SIP signaling messages along with the timestamp, and it will also include all the radio signals that are happening. For example, whenever the PTT is turned on, okay, we are giving all the details like what is the PTT type, PTT status, PTT ID, like this. Okay, so along with the timestamp when exactly they have occurred. And if you select one of these messages, we are also giving the complete message decode on the right side. So these things will help in analyzing the exact messages what have exchanged, and if there are any parameters are wrong, or what exactly we have sent and what exactly we have received, why the call has failed. So this this message decode will completely help in analyzing the failures. And apart from this, we also have like a load generation and a background call generation capability, wherein like either we can create multiple controller working positions and generate hundreds of calls simultaneously to perform the load testing. Okay. And we also have some automation features, like wherein we can apply the PTT and squelch on a particular call on a periodic basis or on a random basis. Okay, so you can define all these intervals, and you can just start the call. It will the PTT and squelch will be happening simultaneous, as per the configurations. So that will help in some kind of automation. And one more important point is we are also detecting the pilot and controller pilot induced synchronous transmissions. So these are detected entirely based upon what information it is conveyed in the RTP packets. So for example, we say pilot induced SCT whenever the PTT flag is set in the received traffic in the sense the traffic that is coming from the GRS. Whenever the squelch bit is set and ACT bit is set, but PTT bit is not set. So it is like it is actually indicating there are multiple aircrafts which are doing the squelch simultaneously. In case of controller pilot induced ACT, it will be like the PTT bit is also set, squelch is also set, and the ACT bit is also set. So actually this scenario will happen whenever the receiver catches the adjacent transmitter's voice, and it is setting the squelch also, when the PTT activation is also indicated by this radio. So here in this diagram, pictorially we are trying to depict like what we are trying to claim, like multiple controllers and ground radio stations can be simulated. So as you can see, in a single instance, we have created like a multiple controller working positions. And on the other side, when we are simulating the GRS, so we are simulating multiple ground radio stations, and we can have all types of radio calls across them. So in the next slide, we'll just highlight the recent ED137 1C features that have been introduced in the specifications. Basically, these include like radio receiver multicast operations, cell call tone transmission. Okay, and they have also introduced one more PTT type, that is test PTT, and the radio version has been upgraded to radio.02. And there are some reservations for PTT ID, like PTT ID 63 is reserved for cell call tone transmission, and PTT IDs 60, 61, 62 are reserved for PTT keying from non-VoIP source. So all these features have been embedded in the software. So all these features can be simulated to verify the functionalities of the device under test.
ED137 telephone emulator is just like the ED137 radio and CWP emulators in that it is software only, and we can supply it as just software that you can install on a notebook PC, and all of the features, the easy-to-use features associated with the ED137 emulator are radio emulator, radio CWP emulator come with the ED137 telephone. Same thing. You can install this on the same PC or a separate PC. Of course, we know what ED137 telephone is. It's for communication between CWPs and for voice communication. And there, voice communication is extremely important in this air traffic control. It's the driving force for communications between the air traffic controller and the pilot. So, and also the air traffic controllers themselves. There are many features in the telephone emulator that allow you to preempt and prioritize telephone calls, because you want to be able to hand off calls as the airplane is moving through different airspaces. So this telephone emulator is rich in the features associated with telephone communications, and it's identical in terms of operation. The GUI is identical. It follows our MAPST architecture, which is you can actually, just like in the radio emulator, the telephone emulator can also emulate single, multiple, hundreds, thousands of actual calls. Of course, you won't need the thousands, but it's possible to do that as well.
Okay, so here again, the telephone emulator, it is going to simulate the controller working positions as per the specifications like ED137 2B and 2C versions, that is for telephone interfaces. We can simulate multiple controller working positions, and each of these controller working positions can also have a unique IP addresses. So we support this IP spoofing mechanism to have a unique IP addresses. And here, like again, we have the same kind of traffic actions, whatever we discussed just now. And the load generation and background traffic generation is also possible. Like we can make thousands of calls, simultaneous calls to check the performance of the network or the device under test.
Okay. Yeah, the profiles, since I did the profiles on the radio and CWP, the telephone emulator CWP profiles are very much similar to the way the radio worked. Same type of features and capabilities. You have the profile gives you all of these specifics associated with a particular CWP. This is particularly for the telephone, so you will have all of these call types, instantaneous access, direct access, indirect access, monitor, all these call scenarios that allow you prioritization, preemption, ring down, the telephone features that make communications instantaneous and quick. So all of those capabilities are here. You can emulate all of those, and similar to the radio emulator, you can also introduce impairments, packet loss, latency, duplication, and so on.
Here again we are trying to show this the call generation feature. Okay, so you can see the call graph shows what kind of call it has been made. For example, we are detecting what kind of call it is, DA IDA call. And we are also measuring some call setup time, and we are listing out all the messages that have exchanged. Again, we have the message decodes. So similarly, like in A to ground, we have the SIP call control.gls that is going to simulate all kinds of ground to ground scenarios. And we also have the options here like transfer, re-invite, and put the call on hold. We even have the option to send traffic and introduce the impairments. And apart from these features, I would also like to introduce like we can have multiple scripts selected here, and they can be run either sequentially or randomly. And the individual scripts can also be run for multiple iterations also. So we can configure these iterations, and if we just click on the start button, it will keep on running the calls one by one, and as and when it progresses, the completed iterations are also displayed here. And apart from this one, we have also the scheduler capability, wherein a particular test can be run at a particular time of the day or a week or a month. Okay, and it can even be configured to run how many times or how much duration it needs to be run. Okay, so that will help in automating the test cases without the presence of actual the test engineer there. And again, in this picture, we are again trying to simulate to show we can simulate multiple controller working positions, and we can simulate all these different types of telephone call types like DIDA call, instantaneous access, single destination voice call, multi-destination, monitoring calls, and all. So recorder emulator, again, it has the same specifications as telephone and radio. Here in this diagram, we are trying to show the recorder interfaces that we can emulate at the controller working position or at the ground radio station, or we can even act as the recorder itself to receive these streams and record the audio and the call detail records. And all these emulations are according to the ED138 4B and also the 4C specifications. Okay, and yeah, the specification defines 3 different types of audio transport for this RTSP streams or the recording streams. We support all these things, and those are basically like embedded binary data, either or it could be like independent TCP or it could be independent UDP. So user will have all these options, so he can make the choice when he is configuring the profiles. So in the next slide, we'll talk about the use cases. Okay, say for example, in these 2 use cases, we are trying to test a recorder. Okay, recorder is the device under test. Okay, so what we can do is using this MAPST ED138 recorder, we can emulate either the CWP node or the GRS node, and we can create all these or simulate the RTSP sessions, the recording sessions towards the recorder, and we can verify all the functionalities of the recorder and also the capabilities of the recorder, like how many calls it can record, how many calls it can handle properly, whether the recorded voice is proper and all. So all those scenarios can be simulated from these controller working positions or the ground radio stations. And in the second slide, we are showing like how we can simulate the recorder streams for ground to ground sessions. Yeah, in the next slide, we have the third case wherein the MAPST ED138 recorder is acting as a recorder itself. And now we are actually trying to test the controller working positions or the VCS, which will have this recorder interface. Okay, so these are the device under test. Now they can establish the recording session towards the recorder. Okay, and whatever the streams they are sending, so those will be recorded, both the audio and the call detail record. So later we can verify all these sessions, whether we have received all the information. And since we are getting this message graphs and also we are displaying the message graphs, during the runtime also we can verify whether we are getting the appropriate messages at the appropriate time. So similarly, we can validate the recorder interface at the ground radio station against the simulated recorder. So the profile mechanism is also used in this recorder emulator. So you can see here right now, in this case, we are simulating a recorder interface at the controller working positions. So you can see like the recorder address, what is the RTSP IP addresses, and what are the PTT types that need to be simulated on the call and all. Okay. So either you can simulate the air to ground call or the ground to ground call for the recording session. And apart from this, we can, one of the advantage of this application is it can easily add all the custom call record data properties and also the operations easily. And on all the recording sessions, we can record the audio, and the call detail record data can be dumped to the CSV for verification. And we also have some automated scripts wherein it can simulate the air to ground calls and also perform the PTT and squelch actions periodically or randomly. So this is the call generation window where we are highlighting, we are showing a recording session that is established between this controller working position and the recorder at 1.59 IP addresses. So you can see the RTSP messages listed here. And when you click on these messages, we get complete decode of the RTSP messages. So you can see here, these will talk about the RTSP message, and this is the body which will carry all the call detail record information. For example, what is the call reference direction, priority of the call, calling number, and call number which is being recorded. Okay. And similarly, we have option to run multiple scripts either sequentially and randomly, or we can run a single script for multiple iterations also. And again, like all those automation features will get applied to all our across all our emulators. Okay. And we can also create like hundreds of controller working positions or the GRS, and create multiple or a bulk recording sessions towards the DUT to verify the performance.
So the key updates we want to tell you since our last webinar, when we also went through pretty much similar slides, is that all of our emulators, radio, telephone, and recorder, are being validated against the voter tool. I think we're almost done with that, but we're not quite. So we're going to be announcing that soon. And so all our emulators, all three of them, with the latest standards, we'll be announcing that our standards are voter validated. In addition, we are keeping track with all of the standards releases, ED137B and C version standards. Of course, we're all up to date on that. In addition, you can actually pick which standard you want to run against, and this is somewhat useful for many vendors since they may not have yet implemented a later version. They may have the B version and not have implemented the C version. So you can actually pick the version that you want to execute. So all of our radio, telephone, and recorders work that way. And one important thing that we just did recently, last year, we participated in the FAA VoIP interoperability event. As I mentioned earlier, interoperability is an extremely important aspect for ANSPs, EUROCAE, as well as the FAA. It provides the economic driving force for these providers to select any equipment from any vendor and guarantee that that they are standards-based and that they work together. And at this event, we played an important role in using our emulators. We supplied something like maybe 15 or 20 emulators, and we used our packet scan as well. We'll talk about packet scan in just a few minutes, which is our sort of Wireshark on steroids, like a platform that allows us to monitor and also collect call record statistics for all of the sessions that are established, the PTT sessions and so on. So these are the important things that have happened since our last webinar. And that was a very, we did get a commendation letter. We're kind of proud of that. So our most manufacturers out there are using our equipment to for emulation, for testing, for performance testing, for bulk call testing, and so on. Okay, that kind of concludes our first part, the actual body of the emulators, the radio emulators, the telephone, and the recorder interfaces. We're going to talk a little bit about our air traffic monitoring solutions, sort of the ED138 realm. And here we're going to talk about two products. They are Packet Scan and NetSurveyor Web, as we call it. And here is a depiction of where these products kind of sit. Our Packet Scan is like I said, like Wireshark, and it sits somewhere in the IP domain, and it can work off of a passive port. For example, if the port is repeated, or if it's off of a mirror port, and it's a very it can handle wire speed traffic, so it can operate at not only off of a simple on a notebook. Again, it's only software, so you can install it on a notebook PC, or we can provide it as an appliance where it can actually. We have an HD version of it that can actually handle tens of thousands of calls. The regular Packet Scan version can handle up to 1,000 calls, or sessions, and it collects this information. And much like Wireshark, it provides a lot of detailed information, drill down information. But not only that, it provides all of the codec capabilities, and in addition, it provides these CDRs to our NetSurveyor Web, where it's a browser-based access, allows you to collect data over long periods of time, assess performance, assess stability, assess a lot of aspects of ED138. Packet Scan, again, is much like our ED137 emulators, and in that it can reside on a notebook PC, or we can provide it in a much more robust environment on an appliance where it can run, the same software can run, and an HD version can run, where it can actually handle wire speed traffic at much higher densities, tens of thousands of sessions, but normally you may not need that. Again, it's a Windows 7 10-based system, 64-bit, very easy to use. Actually, one of the elements of it called PDA, Packet Data Access, Packet, is a very useful feature. We'll show you that in a few minutes. It gives you a more unique drill down. You can listen to audio in real time. A lot of capability like that. In addition, as I said, it can funnel all of these call data records, as we call them, or PTT sessions or SQL sessions, to NetSurveyor Web, which is an Oracle-based software that can collect this, and you can visually see that information. Okay, Srinivas, you want to keep going? The next slide.
Yeah. So basically, Packet Scan can be used to capture and monitor air to ground and ground to ground calls in the ATM network. Okay, so as you can see here, so we are displaying the captured frames. So we provide the frame summary view wherein all the frames will be listed along with the frame details like what are the protocols, IP address, port numbers, and what are the message details like this. So it helps in easy analysis of the messages received. Along with that, we also provide the complete decode of the message right from the MAC layer till to the application layer. And apart from this, we also provide the hex view of each of the individual frames. Okay. And basically, so it has three views: frame summary, detail, and hex views. Okay. So we can capture the calls in real time for the infinite duration. So this is accommodated by having a circular buffer, okay, that will allow you to capture continuously. And the important thing here is we decode all the SIP, RTP, and all the RTP header extension fields defined in the ED137. So you can see the sample here. The base header of ED137 is decoded here. And apart from this, we also have the capture and view filters that will allow you to capture the traffic of interest. For example, mainly like air to ground and ground to ground calls are involved with only SIP and RTP traffic. So, and you can, if you apply those filters, it will just reject all the other traffic and it will just capture the SIP and RTP traffic, which is of interest. Okay. And we can also import and export the Wireshark traces. For example, you have some Wireshark traces captured in the field or somewhere in the network. Okay, if you want to analyze those things, so you can just import those files in the packet scan and use it, import those files and analyze the traffic that has been captured, as we provide a lot of valuable information on those captured traffic. So this is like a PDA, packet data analysis, or we can also refer it as a call summary, wherein in the previous image we showed the frame summaries. Now we are showing the call summaries, which are derived from those captured frames. So as you can see here, the pink line represents the SIP call. Okay, it shows like who is the caller, callee, call start time, duration, and all. And the two black lines associated represent the audio channels for that particular call. And these audio channels provide all the important information about the call, like what is the audio codec used, how many RTP packets have been received, and we provide all the voice quality metrics like MOS scores, packet discarded, missing packets, duplicate packets, the delay and jitter values on each of these audio channels. Okay, and you can also see that a couple of calls have a very good MOS scores, that is 4.2. Okay, but other couple of calls have a very bad MOS scores. You can see here 2.21 and 1.47. Okay, so if you try to just go down this line, okay, you will find the reason why the MOS score has been degraded. Either it will be because of the packet losses or the delay or the jitter introduced in the call. Okay, so right now it is because of the packet loss. So you can see here almost like 25% of packets have been lost. That has heavily degraded these MOS scores. Okay, and importantly, we are calculating these MOS scores for every PTT and squelch iterations freshly. So whatever the score you see is for a particular PTT or the squelch. It is not like a accumulated one. And apart from this, to help the analysis, to analyze the calls in detail, okay, you can just select the call. We display the call graph here. And again, like all the signaling and radio signal messages, whatever have been exchanged are displayed. And by selecting the individual messages, you can get the complete decode of the messages. Okay, and apart from this, we have a lot of other important features. For example, we can play the audio on the call, or we can record it to the voice file. we can save the traces of a particular call, and we can also set some triggers and actions which will actually allow you to define certain filters. Say, for example, you want to filter out all the calls with packet loss more than 1% or any of the calls with MOS score less than 3 or something like that. Okay, so so in a real-time capture, if you have predefined these filtering criterias, then the application will automatically filter these calls as and when these scenarios or when the thresholds are crossed or whenever these scenarios are met. And apart from this, we can also perform a set of actions on those filtered calls. For example, I may want to save the trace of that call, okay, so that I can later analyze it offline, okay. Or we can record the audio on that call if the voice quality is low, or we can even generate a call summary in the PDF or a CSV format, okay. And apart from this, we also have option to store all the call detail records on all these calls, and it can be dumped to the CSV files. Okay, so you have a complete details as an to view in the offline also, or you can share it with your colleagues or like that. So the report. So next section is the net surveyor web. As we discussed, like the packet scan has can also act as a probe, and it can generate these call detail records and send it to a centralized database. Okay, once it is sent to the centralized database, this net surveyor web, which is a web-based application, it can query this database and get all these call detail records and represent them in a very systematic way, where it will allow the users or the people who are monitoring their network remotely from anywhere. I mean, it is just a URL. If you have access to that URL, you can just monitor complete health of your network. Okay, so you can see here all these call detail records have been displayed here, and these drop downs will also show the audio channels associated with the call. We can also play the audio on this audio received on this call, and we also have some quick CDRs where we have a quick links to look at the calls of interest. Say, for example, I want to see only the air to ground calls or the ground to ground calls. Very good examples could be like, I want to see the poor MOS calls or the failed calls which have failed because of signaling reasons or whatever. Okay, so user can define these call detail records, and he also will have the flexibility to define certain filters, or he can define the reports. For example, he wants to see like how many calls have been failed for the last 1 week or so. So it can give a daily report or a hourly report. Okay, so all those things can be configured here. We can provide that time frame during from what to what time we want to see the reports, or we also have some shortcut links like yesterday, last 7 days, like this. Okay, so basically this net surveyor web application is going to help in analyzing your network, complete network health in real time, and also historical, since all the calls have been stored in the database. And as we discussed, like we have two versions here, net surveyor web and net surveyor web lite. So in case of net surveyor web, multiple packet scan probes can feed data to a centralized database, and it is for the larger volume of the calls. Whereas net surveyor web lite, that will be installed along with the packet scan. Okay, so it can store or display the records that are generated or probed by the individual packet scan. So that is like a lighter version. It has a very limited storage. Okay, so it is for a very limited purpose, like when you are analyzing the your network in the lab or something like that, where you are generating very limited calls. So next image shows the call detail view. So you can see here we have listed out all the events, whatever the PTT and squelch events that have been captured. And as I told, for each individual PTT and squelch cycles, we are separately calculating the MOS scores. So you have individual scores for each of the squelch and PTT that have happened on the call. And below, we are again reconstructing those call graphs, and we are also providing this message decodes for remote analysis. And the other good part of this one is the pictorially, it will give all the reports for a defined period. Say, for example, here we are displaying the for a certain days of records here, and a user can define his own KPIs, the key performance indices, like what he wants to see over a period of time. For example, in this graph, we are showing the MOS scores, which is categorized as a desirable CMOS, reach connection CMOS, acceptable or not recommended kind of thing. Okay. And similarly, we have a packet loss. Okay. It lists out the packets with a packet loss less than 14248 calls. Okay. Like this, if the call packet loss is between 1 to 2%, we have a 50 calls here. And for a quicker access, if you want to analyze these calls, say for example, you have a calls reported for 1 to 2% as a 50 calls. If you click on this link, it will going to list out only those 50 calls, so that you can do the further analysis or dig into the calls to understand why the calls have so much packet drops. Similarly, we have a failed calls, so we can user can list out these scenarios, what are the failed scenarios, categorize these failed scenarios, and they will be populated as and when they occur. And other important thing is like this is like something like a non-intrusive monitoring and reporting kind of thing, wherein again you can define the triggers or thresholds. For example, you want to see like whenever the MOS score reduces below 3 or packet loss is more than 1%, you want it to be notified. Okay, so those notifications can be generated in the form of email, wherein we'll send a complete PDF report to the pre-configured email addresses, or we can log the events in the application, or we can even also generate visual and audible alarms.
ED138 specifies a lot of performance metrics, and these metrics are extremely important for the performance of the for the air traffic management. As you know, some of the critical there are some very critical delay requirements. There are voice quality requirements, and today we're just going to show you our suite of equipment that is applicable for the field as well as in the lab. Of course, in the field, what we're interested in is being able to make these measurements on live traffic as it is being transported in the live network. In the lab environment, we're more interested in creating stress scenarios and bulk traffic, and again making measurements over a longer period of time to stress test our element that we are trying to test, whether it be gateways or the radio or the VCS or what have you. So we're just going to go through a few very important highlights. Okay, so this is just a typical network in transition. We can see here two controller working positions. Over on the left, we have a legacy VCS. On the right, we have a VoIP VCS. On the left, we have a VoIP gateway that converts from legacy to IP. And here we have a ground radio station. In this case, it's a IP radio. So in this type of environment, next slide will show you where all of these critical time measurements, according to ED138, these are just a few of the timing points that are very critical. If we go to 2 slides from this, I'll show you what all of these time triggers are. We'll show you this. Go to the next slide, Srinivas. Okay, so these are all of the important events to measure in an ATM network. just to tell you, for example, PTT, of course, these confirmation release to squelch, these are all end-to-end delay, end-to-end voice delay. There are a lot of other important real-time signals that have to be transmitted in critical time. Like, for example, main standby, if you, for some reason, there was a failure, you wanted to transmit over the standby, all of these things have very critical time requirements. So it's just to give you an idea, this is just a sampling of some of the timing events that are there. If we go back to the previous slide, these are the actual specifications that come out of ED138, and that is the PTT delay, if we go to the top, should be, can go up to 150 milliseconds, squelch can be 150 milliseconds, packet-to-packet jitters, less than 15 milliseconds, and so on. And these are all requirements associated with the packet performance. In the TDM world, they're a little bit more, they're quicker, but these are the maximums that are defined. So one-way voice delay, of course, on the telephone should be less than 150. One-way voice delay over radio should be less than 130. That imposes a certain requirements for these control signals like PTT and squelch, so that you have a real-time conversation. That's obviously what we're after here. Between the air traffic controller and the pilot, we want real-time communication. We don't want any hesitancy there or any kind of double talk, disturbances where one person is talking and the voice doesn't reach the pilot in time and the pilot is confused, and so those kinds of problems that occur in very high latency networks, we want to avoid that. That's why the PTT latency, one-way PTT latency, is something on the order of less than 80 milliseconds. So these requirements essentially guarantee real-time performance, and this is what we want to measure. Okay, and our equipment that we have provided, we have a suite of test equipment that allows us to measure at the analog interface, at the packet interface, and at the and to collect these real-time events as these signals are being transmitted. And at the analog interface, we can have we call our audio analyzer, which has this capability to detect analog events, and those events could be things like PTT, it could be squelch events. These are usually signals on analog radios that are available over certain analog interfaces, like even TTL interfaces or what have you. So we want to be able to detect those signals at the analog interface. So our audio analyzer and another product that we'll show you in a minute, our discrete signal logger, provide that capability. So at the analog interface. At the packet interface, we want to be able to detect these events that are converted from analog to packet, for example, like, and they are normally in the RTP extended header. The packet analyzer allows us to do that. Our packet analyzer is based around our Packet Expert product. So it is a multi, if we go to the next slide, the deployment. So we have two suites of test equipment, one for the lab, as I mentioned, and one for deployment. If you're in the field and you want to make measurements of these critical events that we just talked about, this is the suite of equipment that we have that's relatively portable, and it's accessible via either browsers or a remote desktop or just a straight Ethernet interface, a monitoring interface. So these, we have an administrator that controls all of the actions. The administrator can initiate calls if that's what we want to do. It can calculate that. It can detect. It can command the analyzer, the audio analyzer, or the discrete signal logger, or the packet analyzer, to look for certain events, critical events, the events that we listed in that long table, any of those types of events. And in fact, actually, there's quite a bit more. So any of those events could be monitored, and also you can do voice quality. So a session that involves voice as well as push-to-talk, squelch, etc., we can make those measurements and actually do a voice quality measurement. So there, unlike what Srinivas talked about earlier in packet scan, where the voice quality metrics there are based on the E model, R factor, where the voice quality is derived from the packet flow. Here, we're actually using the actual voice signal, a reference signal, and a degraded signal at two endpoints from the origin to the destination, and we will capture that, do a either PESQ or POLQA measurement according to the standards. So both critical delay, voice quality, and all of those metrics are possible with this deployment architecture based around our portable units that have both analog capability, analog interface capability, and a packet capability. This is just a brief description of those elements. Next slide. Okay, so in the field, where do these portable units go, and how do you control them? So we have a MAPST administrator, it could be a laptop, for example, would be running a master script that is commanding the packet analyzer, the audio analyzer, the discrete signal logger to conduct an experiment, a test, generate a call. Or you could actually monitor a call that is being that is occurring with the real live equipment and just be in monitor mode. But this is where in this type of environment, GPS is crucial. So our units are GPS compatible, and they can detect GPS, or in case GPS is not available, we can also use a PTP, precision time protocol, to drive our packet analyzers and achieve microsecond accuracy. So all of these timing measurements are capable of microsecond accuracy. So here is just a typical environment for our field solution. Okay, our lab environment essentially is the same as similar to our field environment, except that all of the equipment is available in a rack system in the convenience of your lab. And here we provide our ED137 emulators, telephone, radio, GRS, all in an appliance. And these appliances can generate large volumes. And those large volumes of traffic can be used to stress test different elements, like, for example, a gateway, a VCS, a radio, and various other elements. And they can be running up to 200, 300, 400, thousands of calls if it's necessary, and for long durations. Normally, what you would do is create a large amount of background traffic, PTT squelch sessions, and also simulate different types of messaging like main standby switching and so on. You create a script in our emulators and our telephone emulator and our radio emulators. As we talked about earlier, you can do that. You can predefine profiles that create certain message sequences, and those are repeatable. And you can create this kind of background traffic that is very much similar to the real world, in addition to just regular traffic with actual voice traffic. Along with that background traffic, then you want to have measurement traffic. You want to create certain unique traffic that, for example, if you are interested in the PTT delay, and you want to run the PTT delay measurement perhaps thousands of times and make sure that the distribution of the PTT delay is well within the requirements required by your ANSP provider or the FAA. So normally they will say that 99% of the calls should have a PTT delay less than or equal to a certain amount. So you can have some outliers, but the majority of them have to be within a certain distribution. So this is how you would create background traffic, measurement traffic, and run this thing in a stressful environment over long periods of time. And the critical components here, again, are our audio analyzer, which has the analog interface capability, can simulate PTT at the analog interface, or you can use our radio emulators and our telephone emulator to create the emulator traffic if you're only interested in the IP domain. Our event data logger collects these statistics. Our packet analyzer is the one that's doing most of the hard work. It's a wire speed packet detector. Any and all packets of unique nature, like the PTT packet, squelch packet, or whatever you may have, can be detected, time-stamped, and sent to the event data logger. That can happen at both the source and the destination. So the next slide will show you how this is all set up. Okay, so here, the TM-ATM lab solution. This is similar to the environment that I showed you with the field. However, we're showing it a little bit more detail here and all the timing parameters that can be measured and automatically collected and provided. I prepared a short video that shows you how these measurements can be made in a lab environment. We used a lab because it was more convenient. And let's go ahead and play that. It's a short video.
Welcome to GL Communications' demonstration of our TM-ATM test suite. This test suite is used for time delay and voice quality measurements for air traffic management networks. Objectives of this demonstration are to show the signal delay calculation, voice delay calculation, and voice quality testing for push-to-talk cycle and squelch cycles. On the screen is the lab setup diagram of our TM-ATM solution. Let us go over briefly the functionalities of each of the components. MAPST Administrator is a GUI-based client which can connect and control multiple GL servers. All the tests and actions are driven by MAPST Administrator. At the end, MAPST Administrator calculates delays, queries for voice quality scores, and generates CSV results files. Along with this, we have in the diagram the MAPST ED137 radio controller working position emulator and MAPST ED137 radio ground radio station emulator. Between these two emulators, we will place air-to-ground calls, background as well as foreground calls. We will perform push-to-talk actions, squelch actions, and record audio to files. There are two packet analyzer units equipped with GPS devices. Packet analyzers are in line with the CWP emulator and the GRS emulators. These two packet analyzers are in timed synchronization via GPS. The packet analyzers filter and forward the packets of interest. For example, in this case, the packet analyzers will tap the push-to-talk events, squelch events, and voice events. Filtered packets will be time-stamped with respect to the GPS and will be forwarded to the event data logger. There is also an IPNet simulator connected in line between the CWP and the GRS emulator's traffic path. This IPNet simulator can introduce delay, packet loss, jitter, and other impairments into the defined stream to simulate real-world network effects. Next is the event data logger. The event data logger receives the filtered packets from packet analyzers, decodes those packets, and generates notifications with GPS timestamps to the MAPST administrator. Now we will demonstrate the delay calculation and voice quality measurement test suite. The objective here is to place 100 calls, out of which 99 calls will be background air-to-ground calls and 1 call will be a foreground call on which we will measure the delay and voice quality. This is the MAPST Administrator application. Click on Start Testbed to get started. We will wait until all the servers are initialized. The probe init success on the screen says that all the servers have been successfully initialized. Here we have added 100 entries. Each entry simulates an air-to-ground call. We will place 99 background calls and then one call on which we will measure the delay and voice quality. First, we will wait until all the 99 calls are established. We will verify this with the help of our packet scan application. We can see that 99 calls have been established successfully. On these established calls, PTT and the squelch are keyed randomly. We will place the first call and we will measure delay and voice quality on this particular call. Now let's show the logs section, where all the results will be logged. Here we can see that for the filtered frames, we are getting notifications with the GPS timestamps in terms of nanoseconds. Highlighted one is a PTT delay, and the next one is the voice delay for the PTT cycle. Here is the voice quality POLQA results from the voice quality tester, and that is the end of PTT cycle. Next, the highlighted events are for squelch cycle. On the screen are the events of squelch cycle, the total squelch delay and voice delay for squelch cycle. 0 milliseconds is the PTT cycle delays and 5 milliseconds is squelch cycle delays, as we have introduced 5 millisecond delay in IPNet simulator for squelch. Now let's show some iterative test, wherein we will configure a test call for 5 iterations. On the test call, PTT and squelch will be done 5 times. Delay calculation and voice quality testing will be done for all iterations. Results will be logged to the CSV file. From the log, we can see that the call has been started successfully, and you can see that PTT and squelch iterations are set to 5. And here is the beginning of the first iteration, the events and results of PTT cycle. The events and results of squelch cycle. So similarly, the test will be repeated for all the 5 iterations. Now we are on the 5th iteration, which is about to complete. Here we have finished all the 5 iterations and the call has been terminated successfully. Now let's view the results. The results are logged to the CSV file. On the screen, you can see for 5 iterations the PTT delay, voice delay, recorded voice file name and path, voice quality score for PTT cycle. Similarly, the results have been logged for squelch cycle.
Okay, thank you, Vikram. He's the one who did the video for us. And also thank you to Nagaraj, who helped us with that video. And thank you, Srinivas, you did an excellent job. But we appreciate everybody attending this webinar. Thank you. I hope you got a flavor for the tools that we have. We thank you for your participation and appreciate it. And give us a call if you're interested in these products. We'll be happy to show you a real demo and give you a personal presentation. All right? Thank you.